Okay, welcome back everybody. So this will be our second part of the lecture for Thursday, January 6th. So we're going to start looking at probability, all right? So this is going to be part one of probability. So probability, normal distributions, things like that are going to take up a good part of the rest of February. So this is going to be part one, and we'll pick up part two of basic probability next week. Sorry, get my. So before we get into probability, just a little bit of housekeeping, where we are in terms of our schedule, right? So here we are, the week of February 3rd, right? We just did the second lab. We're on to quiz 2. Originally, I had lab 3 to be set up for next week, okay? But I think the way we're running a little behind, that's my fault in terms of getting through the lecture material. I think what I'm going to do is push back lab 3. I can't push back 1 week because that's the mid-semester semester break. So I think I'm going to push it back to the week of February 24th. Again, this way, so we could, I'm trying to present the material in the lecture before we deal with it in the lab. And lab 3 is going to deal with a little more of standardization and normal distribution and things like that. So the good news is, right, no lab next week, right? But I'll give you guys a message later on. Again, we have our midterm set up for Thursday, February 27th. So I'm going to talk a little bit about that. Right, so the midterm is going to be done on Moodle. It's going to be set up like a quiz, kind of like a long quiz that you've been doing so far in the class. So the way it's going to be set up is going to be on February 27th, but you're going to have the complete 24 hours of that day to complete the exam. Okay, so the midnight on February 27th, all throughout the day until the midnight ending Thursday, February 27th. So you have 24 hours to complete it. It won't take you 24 hours, don't worry. Probably going to take you 2 to 3 hours kind of thing. So I will be hanging out during regular lecture time, so 8 to 11. I'll send out a link. We'll talk more about this in detail later, but just give you a general idea of what I'm thinking. That you can ask me questions, or you can send me an email throughout most of the day if you have any questions. In terms of the questions themselves, right, it's going to be about 40 to 50 questions, depending on how long they are, but there won't be any more than 50, won't be any less than 40. Note that you might be required, or you probably will be required, to use either Excel or JASP to answer one or more of the questions, right? So keep those programs handy. What type of questions should you expect? Well, it could be various formats: multiple choice, fill in the blank, short answer are going to be the majority of them. I don't think I have any matching or anything like that. I might be the odd matching as well. So relatively short format questions, some calculations. Material that you're going to be responsible for is going to be all the lectures up to and including lecture 5, which is probability. Right? So we're doing probability part 1 right now. So the midterm, the stuff you have to study, is going to be all the lectures up till basically the end of next week's lecture, which is probability part 2. And to give you an idea of the type of questions I'll be looking at, right, I'm going to set up a practice exam for you guys to have a look at. And so I should have that ready for you within the next week or two. But I'll give you a note when it is up and ready. Okay, so let's get into probability itself, right? Probability is used for a whole bunch of things, or try to determine the likelihood of some event happening. It's used all across different types of businesses and jurisdictions, things like that, right? All the way from auto insurance, right? How likely is a person to get into an accident, or what type of accident based on some characteristics. Crime prevention, right? How do we know where crime is going to occur, where it's not going to occur, where there's a higher probability of crime than another place? Super Bowl advertising, I'll show you an example of that with beer tasting. And win at cards, right? Probability, gambling, a lot of it has to do with simple chance. Not all games, some games have other types of probability, but these are all different examples of things in life that have to do with probability. So we hear probability statements given out all the time, right? Advertising, 4 out of 5 dentists, 80% recommend Sensodyne, for instance. You have a 40% of catching a cold over the winter, right? 4 out of 10 chances. Another statement, 9 years out of 10, the river freezes up before January 15th, so a 90% probability. We have a white Christmas, 50% or half the time, right? So all of these statements are describing the likelihood of some specific outcome or event occurring. That's basically what probability comes down to. Now I'm a trained hydrologist, which means I study water. So a big probability, a big role that probability has in hydrology is trying to describe the chance of a certain river flood event occurring. So you might hear, right, a lot of times something like a 1 in 100 year flood event, right? What that 1 in 100 year flood event describes is not that that particular height of the river is going to occur every 100 years exactly, right? But that instead there is a 1 in 100 chance or 1% chance that the river or stream or whatever will achieve that height or that volume on any given year. Okay? So that's just another example of probability. So you might be already asking yourself, well, what does really, Chad, probability have to do with spatial statistics or analysis? Well, as we'll see later on in the course, is that we're trying to figure out, a lot of times using probability, what is the likelihood of seeing some spatial arrangement of some characteristic across the landscape, right? We'll be talking a lot about clustering later on, right? So what's the likelihood of seeing a particular data set being clustered? What's the likelihood or probability that it would be peripheral? What's the likelihood that's going to be in a nice, perfectly uniform grid like this? Or is it going to be straight, radial, dispersed? What is the likelihood that we randomly come across one of these particular types of spatial distributions, right? And not only spatial distributions, but the form, right? The spatial arrangement of something, right? Which also has to do with the interactions and also has to do with the patterns. What are the probabilities that we're randomly going to come across a certain arrangement of some surface feature, whether that be a natural feature or a human-made feature? So like I said, we're going to be looking at a lot about the likelihood of finding a certain clustering pattern. And so later on in the labs and in further lectures, we're going to be looking at something called the Moron's Index or Moron's Eye. So the Moron's Eye basically tells us the likelihood that we're going to see a certain pattern of clustering within our data. So we can either see a uniform spatial pattern, or we can see a clustered spatial pattern, or we can see a random spatial pattern. And so this curve here is showing us the assumption of the probability of finding each of these spatial patterns. So a much higher probability of coming across a randomly arranged data set compared to much lower probability coming across a completely uniform spatial distributed data set, which is also greater than the probability of coming across a highly clustered data set. But we'll come back to that later on. First of all, we're going to get into a little bit about basic probability. So let's first look at some examples. So probability, again, is the likelihood of some event occurring. So let's just do a little quiz here. What's more likely to happen? Dying by a bee sting or dying by drowning? So by these numbers here, right, dying by a bee sting, you have one chance out of about 72,000, right? Which is much lower chance compared to drowning, which is about 1 to 9,000. So in this case, the 1 is the drowning, and then the 8,942 are the possible occurrences. So the larger the number on the right gets to the number to the 1, right? The lower the likelihood or the probability that that event is going to actually occur. Okay, do a couple more examples here. What's the probability of getting a hole in one or bowling a perfect 300 game? What's more likely to happen in terms of probability? Well, let's take a look here. No, it's actually a higher probability for getting a hole in one. So yeah, out of every 5,000 chances, right, you got about 1 chance of getting a hole in one. Bowling is a little different, right? On average, right, for every 11,500 games you're going to bowl, you're going to get one that's a perfect 300 game. Another example here, probability. What's more likely to happen? Die by fireworks or being hit by a meteorite? Well, they're both relatively remote, right? But die by fireworks is slightly more likely to occur compared to being hit by a meteorite. Although, right, people have very close encounters, right? So this is a lady back in Boston a few years ago, I think, laying in bed. Meteorite came right through her roof, through her ceiling, and luckily she was sleeping on the other side of the bed, because if that would have hit her, she would have been one of those statistics in terms of probability. Okay, so probability can be used for a whole bunch of different things. Just give you an old example here. Near Super Bowl time, I don't know if any of you guys really follow Super Bowl, but this was a promotion way back in the day. I think it was back in the late 70s and the 80s, in terms of an advertisement of a specific type of beer. So they basically did a taste test between 2 different types of beers, and they're trying to find out the probability of some outcome. So this is for a 1981 Super Bowl ad. So this is a blind taste test between 2 beer types, Schlitz and Michelob Live. It was done live during the Super Bowl. So they had 100 people, all were Michelob drinkers, right? And they basically did a taste test between the Michelob and the Schlitz type of beer. And what they're doing is known as a binomial experiment. So binomial experiment in this case has a fixed number of trials. In this case, the number of trials, N, is equal to 100. So 100 people did the taste test between the 2 different types of beers. Each of those taste tests, each person that went up there and drank the 2 beers, you have to pick which one you like better, right? Only 2 possible outcomes. You have to pick whether you like the Schlitz better or the Michelob better, right? So this is where the binomial comes into play, right? There's only 2 possible outcomes, okay? In this case, the probability of success, and success in this case being which one are you going to choose, they're assuming that it's 50-50, okay? And a key thing is that all the trials are independent to one another. What one person picks does not have any effect or any bearing on what the next person is going to pick in terms of whether they like Michelob or Schlitz better. So you can actually run the numbers in this binomial experiment and see what the probabilities are of getting a certain result of people that are going to pick Michelob versus the Schlitz. So this is here, the top graph here is showing us the probability in decimal form. So this is 10% at the top here, 0% at the bottom here, and this is the outcome. So maybe this is the number of people that picked Michelob. So going from 0 people picking Michelob to 100 people picking Michelob, we can see that at the extreme levels, 0 or 100, is basically a 0% chance that you're either going to have no people picking Michelob or all people picking Michelob. Most of, in terms of probability, most of the likely outcome is somewhere in the middle, right? With the highest outcome being 50 right down the middle. So again, this is what's called a binomial experiment. So you can go to this calculator down here, and we can run the numbers itself. We can set up the number of trials equal to 100. We're going to set the probability of success for each be to 0.5 or 50%, and this is the outcome you get. So basically on the right there, they're adding up the discrete probabilities. So you can look at the graphs or you can calculate the table. So if I scroll down here, it's showing me the success is very low until I start to get up into the 30s and 40s. Again, the outcome of 50 people picking Michelob is the greatest, but it's still only about 8%. And then once you get any higher than 70, your probability or your likelihood of getting more than 70 people picking one type of beer gets more and more remote. So some other applications for probability, some things that we probably didn't even think of, right? Speech recognition, right? So you could think about it, each word, right? Like potato, right? There's a certain probability if you start out your word with a P, that the next letter is going to be a vowel, right? And if you have a vowel, the next letter, there's a certain probability that you're going to have a consonant again, right? So you can break this down and you can start to calculate the probabilities if you start a word with a P, what the next letter is going to be. And then once you have that next letter, that's going to affect what the probability of your next letter is going to be. So some of this probability is used, or a lot of it's used in determining speech recognition and things like that. Okay, let's get into a little bit of definitions here. So first definition or distinction we're going to make is between deterministic and probabilistic outcomes. So deterministic is something that's definitely going to happen with a 100% likelihood, right? If you're getting hit by a truck that's going 100 kilometers an hour, it's going to hurt. Well, it's probably going to do more than hurt, but you know that's definitely, if something occurs, it's going to have a definite effect. So that's what's known as deterministic. So an example of a deterministic forecast for weather is it's going to rain tomorrow in Kelowna. This time of year, more likely it's going to snow, right? But imagine it's summer, right? So if you had a forecast of saying it's going to rain tomorrow in Kelowna, that's a 100% chance, right? Deterministic. The other type is probabilistic. And this is usually what we hear in terms of weather forecasts, right? In that it's not whether it's going to rain or not, is that there's a probability assigned to it. So in this case, maybe there's going to be a 70% chance, so a 7 to 10 chance that it will rain tomorrow in Kelowna. So in terms of probabilistic processes, which we're going to look at in this lab or this lecture, there's two different types. The first one is known as random, right? Meaning that there's equal outcomes of all the possible occurrences. So an example is, imagine rolling a die. It has 6 sides, right? We're assuming that it's a fair die, it's not weighted or loaded or anything. There's an equal chance that a 1's going to come up compared to a 3, compared to a 5, compared to a 6, and so on, right? So each of the outcomes has an equal chance of occurring. That's what's known as a random process, right? Another example, and we'll look at some more examples in terms of drawing a certain card out of a deck of 52. So that's random. And then we have stochastic processes. So stochastic processes, all outcomes are not equal in terms of their likelihood of occurring, right? Some things have more of a likelihood of being the result than other ones. So imagine hurricanes in Florida, right? They have a much higher likelihood of occurring during hurricane season, which is September, right? August, September, October, November, much higher chance of occurring during hurricane season compared to in March. So we have unequal weights of possible outcomes with stochastic processes, but equal chance of things occurring with random processes. So just an aside in terms of the language thing and how probability is used. Some of you World War II buffs out there, and it was made into a movie lately called The Imitation Game. But basically back in World War II, when the Germans were sending messages to each other from the field headquarters out to the field and back, They did not want the Allies to intercept any of the messages and be able to determine what they're going to do. So the Germans developed what's known, and this is the machine on the top left here, as the Enigma machine. And so the Enigma machine basically coded all of their messages, right, were just sent out over wire. So it basically scrambled their messages so that anyone that intercepted that message could not tell what the message was actually saying. And so for the Allies, especially the Brits, they put together this team headed by Turing, Alan Turing down here, and that's who this guy's playing in the movie here. He came up with a machine that was trying to decipher or figure out, decode what were the coded messages going out in terms of the Enigma machine. So the Enigma machine, the way it worked is that it had a set of rotors, right? And they were spun around. And so any message that would be punched into a keyboard here would go through this series of scramble combinations. And so what your message would be outputted would be completely different. So if, in this case, if you press T on the keyboard, it would go through all of these scramblings and it would actually output as a G. So you would need to know the code in order to basically back calculate that G actually meant a T. So for the time especially, the very sophisticated way of scrambling the messages. And so what Turing did, and this is actually a picture, it's actually a park where they did this work out there in Bletchley Park, just northwest of England, statue of Turing right there. And he invented what's known, they called it the bomb. And the bomb machine, kind of the decoder machine, consists of all of these, you can see these rotors. And these rotors had 26 positions, one position for each letter of the alphabet. And so what Turing was trying to do, using a whole bunch of mathematics, was trying to figure out the probability, again, kind of with the speech recognition, is if I have a P, what's the likelihood the next letter is going to be an O, so on and so forth. So they're running all of these different combinations to try to figure out what the Germans' message was. And it actually was the start of the first computer. So Turing is often known as like father of modern computing. Okay, so kind of give you some introduction there. Now let's get into some basic probability. So how we can describe probability, right? We abbreviate it by a P, and the probability in this case is event A. Okay, so how to define the probability of event A? Well, we can define it by the ratio of the frequency, or the number of times A occurs, over the frequency of all of events occurring, of all outcomes. So probability of A is equal to the frequency of the event A occurring over all of the possible events. So for an example, right, what is the probability of rolling a 6 using one dice? Right? So each dice has 6 possible outcomes, right? The number 1 is one of those 6 possible outcomes, right? So we can define the probability of rolling a 1 as 1 over 6 equal to 0.167 in decimal form, and about 16.7% in percentage form, which is about, another way to state it, is about 17 times out of 100. Every 100 rolls of the dice, you're going to get a 1, you'd expect it anyways, about 17 times. So this is how basic probability works. So I want to talk now about what's known as statistical independent events. Now, independence meaning that what occurs on one event is not influenced by what happened previously on another event. So an example is flipping a coin 3 times, right? If you flip a coin once, you get heads, right? That doesn't affect what the outcome of the second flip is going to be, and that doesn't affect what the outcome of the third flip is going to be. So the outcome of each of these 3 individual coin flips is independent of one another. So that's what's meant by statistically independent events. So let's go back to our dice here, right? What's the chance in this case say we're interested in determining what's the chance or probability, right? Chance, probability, synonyms basically, of rolling 3 6s in a row. So you take your dice, you roll it once, you get whatever you get, maybe you get a 6, right? Roll it the second time. Whatever happened on the first time does not affect the outcome on the second or third times. So that's what's meant by this independent events. And so if we're trying to figure out the probability of, say, we're trying to figure out the chance of rolling a 6 and then a 6 and then a 6. So we're trying to see what the chances are of rolling 3 6s in a row. We can use what's known as the AND rule. And basically what the AND rule does is that if we're trying to figure out the probability of A and B and, in this case, C, all rolling a 6, we're going to multiply the independent probabilities together. So if we're trying to find the probability of rolling a 6, which is 1 out of 6, and then rolling another 6, again, 1 out of 6, and then rolling a third time a 6, again, that's 1 out of 6. We're going to take those individual independent probabilities, multiply them together, and that gives us our final probability. So you can see that rolling 3 6s in a row here is relatively remote, about 0.5%. So that's how we can figure out the combined probabilities for independent events. Then we have a slightly different type of probability called the dependent, or sometimes called conditional events, because what happens on a previous event affects the probabilities of the event after it. So an example here would be, what is the chance of drawing 2 kings in a row from a deck of shuffled playing cards? Okay, so what's the probability of randomly picking a card from a deck of 52, getting a king, and then what's the probability of picking another king after the first king? So this is different. This is not independent, because what happened in the first event affects the probability of what's going to occur in the second event. So this is how we could write the probability for picking a king on the first pick and a king on the second pick. So the probability of picking a king on the first pick is that, so that's a probability there. And then we're going to multiply that probability by the conditional probability of picking a second king if on the first pick we did also pick a king. So why is it dependent or conditional? Well, let's look at a standard deck of 52 cards, right? So we're probably all vaguely familiar with our standard deck, right? 52 cards where we have 4 suits, clubs, spades, hearts, and diamonds. So our first probability of picking a king, right, since we have 4 kings, the probability of picking a king on the first draw is 4 out of 52. Pretty straightforward, right? So there's our 4 kings right there. Since there's 4 kings and there's 52 cards, right, our probability of picking a king on the first draw is 4 out of 52. So imagine we do actually pick a king on the first pick. So imagine we pick the king of clubs. Now that's going to affect what the probability is of picking a king on the second draw, because now we only have 3 kings left. So instead of 4 out of 52, right, it's actually wrong here. It's actually going to be 3 out of 51, because we've actually taken, since we've taken that king out of circulation, now we only have 51 cards left. So our first probability of picking a king is 4 out of 52. So we're taking, right, we take 1 king, we pick a king. So now we have 3 kings left, and we have 51 total cards left. So our probability on the second picking the king is going to be 3 out of 51. So the total probability of picking a king on the first draw and picking a king on the second draw is determined by multiplying those individual probabilities. In this case, 4 out of 52 multiplied by 3 out of 51 gives us a total probability of 1 over 221, a little under 0.5% of picking 2 kings in a row from a standard deck of playing cards. Okay, let's go back to dice. So imagine you're trying to find the probability of rolling a 4 or 5 on the first toss, right? So we have 1 die, roll it. What's the probability of rolling a 4 or 5 in the first toss, taking that same die, and then rolling a 1, 2, or 3 on the second toss? Right, so for the first probability, right, rolling either a 4 or a 5, right, that's 2 out of the 6 possible outcomes. So our probability of rolling a 4 or 5 is going to be 1/3, right? Then our probability of rolling a 1, 2, or 3 is going to be half, right? 1, 2, and 3 make up half of the numbers on a fair die. So those are our two independent probabilities, 1 out of 3 and 1 out of 2. To determine the total probability, we're going to multiply those individual probabilities together. 1/3 multiplied by 1/2 equals 1/6, right? So we to roll either a 4 or 5 in the first toss and then roll a 1, 2, or 3 on the second toss, there's about a 1 in 6 chance, or 16.7% chance of that event occurring, right? Okay, do some more examples, this time back to the cards. We're back to our 52 deck of shuffle playing cards. What's the probability that you will draw 2 hearts in a row? So your first card is going to be a heart, and then your second card is going to be a heart. How would you determine the probability of that event occurring? First thing we need to figure out, are these independent or dependent occurrences? So think about it. If you go and pick a heart on the first card, how does that affect the probability of picking a heart on the second draw? So imagine, right, on the first draw, right, we have 13 hearts, right? So that's 1/4 of our deck. So the probability of picking a heart on the first draw is going to be 13 out of 52, 1/4. So imagine we pick, in this example, we pick the 9 of hearts. So now we have 1 fewer heart card to possibly choose from in our second draw. So on our second draw, our probability has gone from 13 out of 52 now to 12 out of 51. So how we're going to figure out the total probability? Again, we're going to multiply the probability of picking a heart on the first card, on the first draw, and then multiply it by the conditional probability of picking a heart on the second draw, given that we drew a heart on the first card. So again, we're just going to multiply the individual probabilities. 13 over 52 multiplied by 12 over 51 gives us about a 6% chance of picking 2 heart cards in a row. Okay, so we'll go through about 5 more problems here to illustrate how to go about calculating basic probabilities. Again, assuming that we have a standard deck of 52 cards with 4 suits. So let's start with the first one. What is the probability of drawing a 5 card, right? So of course we look at our deck here. What's the probability of picking any one of those 4 5 cards? So pretty simple probability to determine, right? We have 4 5 cards out of a total of 52 total playing cards. So 4 out of 52 is going to be around 8% of picking just randomly a 5 card out of your deck of cards. Okay, what if we, instead of just picking any 5 card, imagine that we want to determine the probability of drawing a red 5. So now we're just dealing with 2 cards. So now our probability has reduced in half, right? So now we're dealing with the probability 2 cards out of 52, around 4% chance of drawing a red 5 randomly. Okay, let's get into some more here. What is the probability of drawing the Jack of Hearts, right? So there's the Jack of Hearts here, and then the Jack of Diamonds. So basically what we're trying to figure out, right? Probability of first drawing that Jack of Hearts, which is 1 out of 52, right? That's just 1 card out of 52 possible outcomes. And then the probability of our drawing the Jack of Diamonds, right? It's just 1 card, but since we've already drawn 1 card out of the possible deck, now our probability for the second draw is 1 out of 51, out of 52. So to determine this total probability, again, we multiply those individual probabilities together, and it gives us a probability of about 0.03% chance. So a pretty remote chance of picking a jack of hearts followed by a jack of diamonds. So again, we're going to multiply those probabilities together. So this relates to the idea of mutually exclusive events versus non-mutually exclusive events. So if we're trying to figure out the probability of A or B occurring, and there's no overlap, right, meaning that they're mutually exclusive. So you can think of the probability of event A occurring as the area within the circle here. Probability of event B occurring is the area in the circle B here. So if there's no overlap, these two events, A and B, are considered mutually exclusive events. So if you're trying to figure out the total probability of A or B occurring, what you're going to do is just add up the total probabilities of A and the total probability of B, and that gives you your probability. But a lot of times what happens is that we have some overlap in the probability of A and B. These are non-mutually exclusive events. So in this case, to determine the probability of A or B when they're non-mutually exclusive, meaning that there's some overlap between event A and event B, we're going to add up their individual probabilities, but then subtract from those individual probabilities the overlap area. So the probability of A and B occurring. So let's look at this in the context of, right, of question D here. What is the probability of drawing the 4 of spades or a club? So the probability of drawing a 4 of spades, so there's a 4 of spades right there, or a club, so the club suit, right? So we know that the suit, the probability of drawing a club is 3 out of 52. The probability of drawing the 4 of spades is 1 out of 52, but because there's no overlap, in other words, these are mutually exclusive events, we simply add up their individual probabilities to get the total probability, right? So these are, we have mutually exclusive individual probabilities. All you do is add up their individual probabilities to get the total probability, right? So we add them together, and that gives us our final probability of either drawing a 4 of spades or a club, right? So that'd be an example of, right, mutually exclusive events. Probability of drawing, right, club, 4 of spades. There's no overlap between those two events, so we can just add up their individual probabilities. Well, let's look at something a little different when we have a non-mutually exclusive event occurring. So in this case, what is the probability of drawing a spade or a 3? So let's look at the individual probabilities. There's our spades, right? Suit of spades. We have a probability of picking a spade of around 13 over 52, or a 3. So the probability, the individual probability of picking a 3, right, is 4 out of 52. There's 4 3 cards in the deck. But you can see that we have an overlap between the probability of the first event occurring and the probability of the second event occurring. That is, right, the 3 of spades, right, because it belongs to both events. So that's our mutual probability, which in this case, we have to subtract the mutual probability from the total probability. So in this case, we're going to take our probability of drawing a 3 card, which is 4 out of 52, add it to the probability of drawing a club, 3 out of 52. But then from that, we're going to subtract the mutual probability, which is 1 card out of 52. So that's going to give us a resulting probability of about 31%. So again, in this case, right, because we had an overlap in our events, right, we're going to take the sum of both of the probabilities and subtract from it the mutual or non-mutually exclusive overlap probability. So we can think of this as kind of the and versus or rule as well, right? So imagine, for example, if you have a single die, you wanted to figure out the probability of rolling a 6 and then a 5 in 2 rolls. What we're going to do is multiply the individual probabilities. But imagine it's stated this way. Using a single die, what's the probability of rolling a 6 or a 5 in 1 roll? So in this case, we're going to add the individual probabilities. So you can imagine, right, you have much greater probability of rolling a 6 or a 5 in 1 roll compared to the probability of rolling a 6 and then a 5. So when you have and in the question or the statement, often you're going to multiply the individual probabilities. If you have or in the statement, often you're going to add the individual probabilities together. So let's apply this to another problem here for independent events. So again, let's look at this example here. What is the chance of finding somebody in Kelowna that was born in India or the United States? So these are independent events, right? You can't be born in 2 countries. In this case, probability of you're either going to be born in India, the country of India, or the country of the United States, right? So these is an example of mutually exclusive events. There's no overlap between somebody being born in India versus somebody being born in the United States, right? So this is a way we can visualize it using a Venn diagram. Probability somebody born in India is completely separate from the probability of somebody born in the United States. So when we're applying this to figure out the overall probability, say you're going around and you're trying to figure out the likelihood of randomly selecting somebody born from India or the United States, what you're going to do is take the individual probabilities, which maybe for this example, somebody being born in India, there's a 0.5% chance of that. Somebody in Kelowna being born from the United States, 2% chance. Since they're mutually exclusive, we're simply going to add up the individual probabilities to give us a total probability of 2.5%. So in this example, we have a 2.5% chance of randomly selecting from somebody in Kelowna and that person being born from either India or the United States. So often when we see or in the question itself, right, we're going to add those individual probabilities together. And if they're mutually exclusive, right, we can just simply add the individual probabilities together. But what, again, let's look at an example of non-mutually exclusive events. So in this example, we want to figure out the probability of somebody choosing somebody randomly that likes ice cream or somebody that likes soccer in a population of 1,000. So unlike our previous example, when we had mutually exclusive events, right, in this case, we can have somebody liking ice cream and that same person also liking soccer. So that's where the overlap occurs. That's where the non-mutually exclusive event occurs. So again, you can think of it, probability A, somebody liking ice cream, probability B, somebody liking soccer, right? We can see that there's overlap. There's people that like both ice cream and soccer at the same time. So that's where that non-mutually exclusive area exists in our Venn diagram. So let's go to trying to figure out what's the probability. So imagine that the probability of somebody liking ice cream in our survey is 60%, okay, 0.6. And the probability, I got a little graphic here, right? Somebody like ice cream, about 60% chance of randomly selecting somebody that likes ice cream. In terms of randomly selecting somebody and then liking soccer, say it's 20%, right? I don't know where these numbers come from, doesn't really matter. So given those individual probabilities, what's the probability that somebody both likes ice cream and soccer? Imagine in this case, it's 4%. So the way I'm going to figure out in this case of randomly selecting, right, somebody that likes either ice cream or soccer is that I'm going to add up the individual probabilities and then subtract the non-mutually exclusive component to those probabilities. So in this case, I'm going to add 0.6 to 0.2. Then from that, I'm going to subtract the overlapping non-mutually exclusive probabilities, which is 0.04. So that's going to give me an overall probability of about 76% of randomly selecting somebody that either likes ice cream or soccer out of 1,000 people. So again, we subtract the mutual probability. Right? So we added up the separate probabilities from event A and event B, and we subtract from that the overlapping probability. Okay, so we're going to look at now a couple specific probability distributions that we can use to figure out the likelihood of some event occurring. So we're going to look at three types of these probability distributions. One we've hinted at already is the binomial distribution. We're also going to look at in this lecture the Poisson distribution. And then next week, we're going to start to look at what's known as the normal distribution. So let's first start out with the binomial distribution. This is like with the beer taste test, right? Binomial means that there's only two possible outcomes. There's no more than two possible outcomes, right? So it's binary, right? So 1 or 0, there's no other option. It's either rain or no rain, male, female, success, failure, on, off. Okay, only two possible outcomes. If you're dealing with a problem that has only two possible outcomes, it's likely that you're going to use a binomial distribution to figure out the probability. So a couple other things you need to know is that the experiment is going to consist of n repeated trials. In the beer taste test example, we had an n of 100. 100 people did the taste test. And each of those trials, there's only two possible outcomes, right? In our beer tasting example, it was either picking Michelob or Schlitz, right? Either one or another. There's no third beer option. And the odds of one person picking one or over another, or more generally, the probability of success, denoted by P, is the same on every trial. Okay, for every trial of the experiment and trials, the individual probability of it going one way or another is exactly the same. Another key thing is that the trials are independent, right? Meaning that the outcome of one trial, right, either it's the 99th person taking the beer taste test, does not affect the 100th person outcome. So they're independent from one another. Right, so there's a bunch of different ways that we can calculate binomial distributions, right? So this can be applied to things like coin tosses, because coin toss we only have two possible outcomes. So an example that we can use a binomial distribution, right? What are the chances of having 0, 1, and 2 heads, right? What are the chances of having 40 or less heads in 100 tosses, right? That's a problem that we could use a binomial distribution to figure out. So here's a link. I don't know if it's a live link, but I've got the link in other slides here. A calculator, online calculator you can use to determine binomial distributions, right? So imagine, again, another example, kind of similar to the beer tasting example, but imagine, right, you did 100 coin flips, right? You can see you can run the binomial distribution to figure out that there's an 8% chance that you'll have 50 heads after that 100 coin flips and exactly 50 tails. So if I wanted to use, so here's the calculator link right there. So imagine I wanted to use this binomial distribution calculator to figure out distribution of, so I'm going to put in my number of trials. N is 100 trials. Probability of each of those trials is 0.5. So this is the outcome. So again, imagine I flip a coin 100 times. What's the probability of certain outcomes? So I can see that the highest probability is around 50, or is 50, and the probabilities decline pretty sharply, either going up from there or down from there. So here's a table which gives me the exact probabilities of the number of successes. So you can see it's not till I get to about 30 or 31 where I start to get significant, where I can actually have some probability of that of having 30 heads or tails. We go down to 50. So getting 50 heads or 50 tails is the likeliest outcome. And then going down here, getting, say, 70 tails or more gets very remote. Okay, let's do an example here. So a manufacturer, so you guys probably remember these mystery bags of candy from your kid from Halloween, right? It has a whole bunch of different candies in it, like, I don't know, 20 candies or something in it. Dozen different types of candies. So imagine you went out and bought 20 of these mystery bags of candy. And you're trying to figure out the probability that none of those bags would have rockets, half of the bags would have rockets, or all 20 of the bags would have rocket candies. Knowing that in each bag, there's about a 50% chance of finding a rocket candy within a single bag. So the 50% is our individual probability. 20 is our number of trials, i.e. Rn. So we go to our binomial distribution calculator for this example. Instead of 100, we're going to put in 20. We have 20 bags, and then the chance or probability of finding rockets or success in each bag is 0.15. So there I see I get a completely different graph for this example. My highest probabilities is to find three of those bags having rockets within them. You can also look at the table. So if I go down, I can see on the left here, these are my individual probabilities. So I got about a 4% chance of none of the bags having rockets. Very small chance of 10 of the bags having rockets, and 0% chance of all 20 bags having rockets within them. So we can also do this in Excel. So I've put in Moodle a spreadsheet outlining these ways that you can calculate binomial distribution in Excel. So the same problem here. Individual probability of rockets in a bag is 50%. The number of trials is 20. And I've outlined some number of successes, i.e. rockets being in how many bags. Then I've calculated using the Excel function. So the number of successes, so in this case it's 0 bags having rockets. The number of trials is 20. The probability in each trial that there being rockets is 0.15. And I'm going to set it to false because I do not want it to be cumulative. And just in that column there, I have it in percentage. And there's the link to the calculator here. So I can use this calculator, enter my individual probability 0.15, 20 bags, go down and calculate, and it gives me the probability, in this case, of having 0 rockets in my So imagine I'm going to change it now to 10. What's the probability of having 10 bags with rockets in them? So we go back here. I can see that I've calculated, right? Very, very small chance. And then if I wanted to go back and do it for what's the probability of all bags, all 20 bags having rockets in them, I can see that it's virtually 0, right? So 0 being down there. I can actually see in this example, the greatest probability is having 3 bags out of those 20 containing rockets. So here's another link here, which you can actually use to visualize the distribution of your binomial distribution. So in this case, I'm going to set the number of trials. I have 20 bags, so that's a number of trials. Again, the probability of rockets in one bag is 15%. And so this is, right, this is the resulting frequency distribution or probability, which matches what I got for how I calculated in Excel. So you can see basically after 9 or 10, there's very small probability of having more than 10 bags or so in rockets. But now say if I set it to an individual probability of 45%, that changes my distribution. And if I put it to 75%, it shifts it to the right even more. Okay, so same problem, slightly different question here. So if you bought 20 mystery candy bags, what's the probability that 5 or fewer bags will contain rockets? And what's the probability that more than 5 bags will contain rockets? So again, you're going to use your binomial distribution. So let's first look at the probability of having 5 or fewer bags containing rockets. So I can go back to my calculator here. So we're going to have the same probability of success on each trial. That's 15% chance of finding a rocket in any bag. 20 bags again, so that's the number of trials. Number of successes in this case is 5. So we're going to hit calculate. Right, so that's probability of getting exactly 5, probability of getting less than 5. What I'm looking for is this one right here. Probability of getting less than or equal to 5 bags with rockets in them. So that's equal to 0.93269. Right? So the probability of, right, out of 20 bags, each bag having a 50% chance of containing rockets, the probability of having 5 or fewer bags containing rockets is going to be equal to about 93%. Right? So a pretty high chance 5 or fewer of the bags will contain rockets. So let's do this one. What's the probability now of more than 5 bags containing rockets? Yeah. So one way I can do this is that since I've already calculated the probability of 5 or fewer bags containing rockets, which I know is to be equal to 0.93269, since I know that my total probability is 100%, otherwise equal to 1, all I can do to figure out the probability of more than 5 bags containing rockets is take the complement, right? So I'm going to take 1, subtract from that the 0.93269, and that's going to give me a probability of 6.73%. So that's going to be the probability of more than 5 bags containing rockets in my example. But I can go back to the calculator again, plug in the same numbers, 15%, 0.15, 20 trials, number of successes 5. So there I go right there. Cumulative probability of more than 5 successes, 0.06. So here's just another example here, right? So same setup of the question. Now we're calculating what's the probability of 12 or more bags will contain rockets, right? So what's the probability, right, of X? So the number of successes being greater than or equal to 12. So I'll let you guys figure that one out using the calculator on your own. Okay, so the second distribution we're going to look at is called the Poisson distribution. It's a little different. It's a discrete distribution, meaning that it figures out the probability of individual number of events. But unlike the binomial, the Poisson distribution has several possible outcomes, not just on or off, one or the other. There's more than 2 possible outcomes with the Poisson distribution. So how the probability using the Poisson distribution is calculated is this formula right here. Don't worry too much about the formula, but just to show you what it's made out of here. So that U is the mean, right? X is the actual number of successes that are going to occur. That X with the exclamation is going to be our factorial. I'll show you what that is in a bit here. But the P is, right, the probability of getting a certain number of occurrences, X, given that the mean probability of occurrence is given by U. Right, so this is just another way that that equation for the Poisson distribution can be written. It can also be written in this form right here. This is basically just a rearrangement of that, but it's made up of the same 4 terms as before. Let's do an example here. So this table, it's a little, quality is a little bad, but basically it gives us the observed hailstorm frequency over a 35-year period for a region in Manitoba, Canada. So here's the number of hailstorms per year. So 0 hailstorms, 2 hailstorms, 5 or more hailstorms. And the second column is a number of years that each of these occurred, right? So on 10 of those years, we had no hailstorms. On 13 of those years, we had 1 hailstorms. And essentially, if you multiply those 2 columns together, you get the total hailstorms. And here's the probability, observed probability of occurrence for each of these number of hailstorms. So for the probability of getting 0 hailstorms is 0.286. Probability of getting 5 or more hailstorms is essentially 0. So that factorial symbol, if you remember back to high school math, basically when you see a number with the exclamation beside it, basically means that you're multiplying all of the numbers equal to or less than it. So 3 factorial is equal to 3 multiplied by 2 multiplied by 1, which is 6. 5 factorial is 5 multiplied by 4, by 3, by 2, by 1, equal to 120. So for our example here, our n, sorry, the sample size, or the number of trials is 35 years. Our total frequencies is 42 hailstorms. And so that gives us a mean frequency of getting a hailstorm each year of 1.2, which is determined by dividing the total frequency of hailstorms by the number of years. So in the tab in the Excel spreadsheet as well, I basically recreated the data table, right? The number of hailstorms, the observed frequency of years that number of hailstorms occurred, the total hailstorms, calculating the probability for each of those, the mean probability, and then I've calculated using the Excel expression for the Poisson distribution, the probability in this column here. Then I've also done it longhand using this equation here for the Poisson distribution. So again, looking at the hailstorm example in the Excel spreadsheet, number of hailstorms, 0 to 5, the observed frequency that each of those numbers occurred. So 10 years we had no hailstorms, 13 years we had 1 hailstorm. And then at the bottom, I've summed all those up to get 35 in total. So if I multiply under the total hailstorms column, to get that, all I do is multiply what's in column B and column C. So 0 multiplied by 10 is 0, 1 by 13 is 13, so on and so forth. I add those up as well. Now to calculate the observed probability of occurrence, the way I'm going to do that is I'm going to divide the observed frequency for each of those divided by the sum. Note the $sign on the sum there so it doesn't move when I drag it down. So that's how I'm going to calculate the probability of getting 0, 1, 2, 3, and 4. That's the observed probability. I'm using the Poisson to calculate the theoretical probability. So to calculate the mean, I'm going to divide 42 by 35. That gives me an average probability of 1.2 hailstorms in a year. And then I'm going to use all of those to calculate probability using the Poisson distribution. So you can see it's asking in Excel for 3 things here. First is a number of successes. Second is the mean. And the third is, I'm going to set the cumulative to false, so it gives me the discrete probability. So I see if I go down to the next one, right? It's now looking at 1. It's still on 1.2 for the mean. And all those individual discrete probabilities all add up to 1. So you can see if I actually put in true here instead of false, and I drag down, it would do a cumulative probability. So it would add up all the probabilities before it. But since I want the discrete or individual probabilities, I'm going to set that to true. So it gives me the probabilities of 0 hailstorms, 1 hailstorm, so on and so forth. And then in this column here, I'm using this expression at the bottom here to calculate the Poisson distribution. Right? So mu to the power of x over e to mu multiplied by factorial of x. That's essentially what that expression right there. And you can see that the Excel expression and the formula that I determined give the same results. And just on the right there, I've basically made up of a bar column chart of the possible or the probabilities of each of the number of hailstorms, which equals what we see from the previous calculation, right? So for this distribution, I have the greatest probability for this data set of getting 1 hailstorm in a year. Once I start to get up to 4 or 5 hailstorms or more, the probability of getting more than that gets very, very remote. So this is how we can use the Poisson distribution. Do another example here. So imagine that the average number of goals that a hockey team scores per game over a season is 3. So that would be our mu. So that's our average, 3 goals per game. Say we wanted to calculate the probability that the team will score, right, 0 goals, 1 goal, 3, 6, or 9 goals in any one given game. So again, we can use the Poisson distribution to determine that. So I can go to the calculator here. So say I wanted to figure out the probability of the team scoring 0 goals in the next game, given that the average number of goals previously is 3. So if I put it into the calculator here, I can see that the Poisson probability is equal to 0.0497, about 5% chance that the team in the next game will score 0 goals, given that on average they score 3 goals per game. So same setup to the question here. Imagine that the average goals per game a team scores is 3. What is the probability that the team will score more than 5 goals in their next game? So in other words, what's the probability of getting more than 5 successes? So again, we can go back to our Poisson distribution calculator. There's a link to it right there. So 5 is the probability I'm trying to figure out for. 3 is the average rate of success, the average number of goals scored. So there is the probability in the next game that that team will score more than 5 goals. So 0.083, so about 8.4%. Okay, so let's apply the Poisson distribution to a spatial data set. Okay, so imagine I have some survey data. So I'm going to look in here. Imagine I have a satellite image of a campground, and I've split that campground into a grid. And that grid consists of 400 individual grids or squares. And imagine I go along, or I have some algorithm, count how many campers are in each of these individual squares. And this is what my results are. So here's my results for the number of campers. So for all of my results, I have 278 of the squares out of the 400 squares having 0 campers in them. 92 of the squares have 1 camper, 25 of the squares have 2 campers, so on and so forth. So the same kind of idea here, the total campers, that's calculated by multiplying the value in the first column by the value in the second column. So 0 multiplied by 278 gives me 0. 1 multiplied by 92 gives me 92. 2 by 25, 25. Again, I calculate my sums at the bottom here. So I have 400 squares, and I have a total of 160 campers. And to get my average rate of success I'm going to take, right? The rate of finding a camper in a grid. I have 160 total campers. I have 400 total squares. So that gives me an average rate of success, in other words, mu of 0.4. So this is another tab in the Excel spreadsheet. So there's my number of campers, the number of squares that number of campers is found. There's my sum at the bottom. So we're going to multiply the values in the first two columns to get the total number of campers. And there's my observed probability of occurrence, right? 278 divided by a total of 400. And here's my mean probability of occurrence. In this case, 160 campers divided by a total of 400 squares, 0.4% chance. And I'm going to use the same expression in Excel to calculate the individual or discrete probabilities. So you can see here that my greatest probability is finding or randomly picking a square with no campers in it. You can also see that the predicted Poisson probability of occurrence using the Excel expression is the same as that given by the longhand calculation. So one thing we can use the Poisson distribution for is to try to figure out whether the number that we're finding is random or not. And the way we can do that is we can compare the calculated Poisson distribution probability versus the observed probability, right? So this is back to our example, the number of campers observed in each of those 100-meter grid squares. So these two bars, right? So 0 campers, 1 camper, 2 campers, so on and so forth, is comparing the probability distribution from the observations themselves, compared that to the Poisson theoretical distribution. So here I can see there's a pretty good agreement between the observed probability and the calculated Poisson probability. So that indicates to me that the spatial arrangement of campers in this case is relatively random. So another way that I can compare the observed probability versus the predicted Poisson probability is to do a straight scattergram or XY plot. So I can see, right, the values line up pretty close along the X to Y being the same line, that dashed line being there, again indicating that I'm probably dealing with a relatively random distribution. So just to show you what's being plotted here in the Excel spreadsheet, there's my predicted Poisson distribution in the blue. There's the observed probability in the orange. So again, you can see a pretty good correspondence, which is also shown in the scatter plot. Okay, so there's one more example, which I'll let you guys work on in the Excel spreadsheet, so you can do what I've shown you already. This tab is called Poisson_car, right? So imagine you went out and you went to different parking lots in Kelowna and you surveyed how many BMWs were in each of those parking lots. So what you can do in this case, right, because there might be 0 BMWs, might be 1 BMW, might be 2, might be 5, there's more than 2 possible outcomes. So this is an example of where you cannot use the binomial distribution. You have to go with the Poisson distribution. So to figure out the probability of finding 0 or 2 or 5 BMWs in a Kelowna parking lot, you can use that expression in Excel, which again is exactly gives you the same output as the general expression right there. So I already showed you these expressions right there. So this is basically how you can calculate these in Excel. So a little bit of homework for you guys, get some practice using the Poisson distribution, right? What is the observed probability of finding 3 BMWs in a Kelowna parking lot? And what is the theoretical or Poisson probability of finding 3 BMWs in a Kelowna parking lot? So Giving you today a little bit of basic probability with a little bit at the binomial distribution and the Poisson distribution. The next distribution, which we'll look at next week, is referred to as the normal distribution. Okay, so again, different assumptions compared to the binomial and the Poisson, but this is what we'll look at starting next Thursday. Okay, so I'll leave it off there for today. You guys have a good weekend, and I'll be in touch with you next week.